Okay, the next problem, number 9, gives us a velocity time function here of a particle moving along a line and wants us to find the displacement. We know the displacement is the area underneath the curve, so we could quickly sketch a graph of this. This is a parabola that opens down. I don't know where the vertex is, but let's just say it looks like this. We want to find the area underneath the curve from 0 to 6. So let's say we could graph this exactly if we wanted, but we're trying to look for this area right here. Now, the only way that we're going to be able to do this one is with the calculator for now. So let's pull out the calculator and let's plug this in. We'll go to alpha window. We'll go to function integral, which is 4. We'll go from 0 to 6 of the function negative x squared plus 5x minus 6 in terms of x. We're using x for t, obviously. And that gives us negative 18. So here's what the graph actually looks like. I didn't graph it very well, obviously, but what it's looking for is the area underneath the curve from 0 to 6. So 1, 2, 3, 4, 5, 6 is right here. So it's looking for this area right here and this area, and then there's a little bit of a positive area, it looks like right there. So you basically have a negative area here. So let's say that's negative 20. Let's say that's, negative 2, and let's say this is positive 4. Then you'd get the negative 18. Just making up numbers. But that's what that is. So displacement is the net distance covered. So it turns out that in the first branch right here, if this is a velocity time graph, it turns out that the velocity is negative, which what that means is, let's say this is positive and this is negative. That means you're moving in the negative direction along this curve. And then the velocity is decreasing. So you're going to start to slow down to 0 basically. And then at this point right here, you change directions and you start heading to the positive for a little bit, and then you change it up again and start heading back negative as time goes on. And it's in that process, how much distance have you covered is a different question from your actual displacement. But to find your actual displacement, all you do is do the integral, because the area underneath the curve in this case, depending on what the units are, let's say the units are feet per second on the velocity, and let's say the units on time are seconds. When you multiply, you get feet. So it turns out the area underneath the curve gives you the displacement, which is the location you're at, basically. Next problem is problem 10. It says 2 cars start at the same time and travel in the same direction along a road here. The velocity is in kilometers per hour as a function of time. All right, it says velocity car A is given by the solid blue curve. So here's A, and then here's B. Which car attains the larger maximum velocity? Well, it told us that this was a velocity time function. So the largest velocity is reached by the red one, which is B. And then which car stops first? Well, stopping in this situation would be where the velocity is 0. And the velocity is 0 right here for the car B and right here for car A. So it would be car B. All right, then the last question is which car travels farther. Travel here would be displacement, which is distance. This is in kilometers per hour, and this is in hours. So when you multiply this, you get the area underneath the curve, which is kilometers per hour times hours. The hours cancel and you get kilometers. So if you find the area underneath the curve, you're finding how much distance is traveled in kilometers. So obviously the blue one, A, has more distance or more area underneath the curve, therefore more distance. So we would say A for that one. Next question says a car initially going 55 feet per second brakes at a constant rate, coming to a stop in 8 seconds. So I'm going to do a velocity time function here. Velocity time function would be we're going 55 feet per second and we're subtracting some acceleration times time. Now that might be confusing, but the acceleration, the units on that are in this case, feet per second. So the acceleration will be feet per second squared. When I multiply that by seconds, what happens is the seconds cancel and I get feet per second, which is a velocity. So it turns out if you look at the units, you can see why multiplying acceleration times time gives us a velocity, which is what we want for this equation because it's a velocity time function. So if you look at a graph of this, which might help, here's a velocity, here's time. We start off at 55 feet per second and we're going to eventually go down to 0 right here. And it says that happens in 8 seconds. So we know that this value for t is at 8 seconds right there. And I'm just going to find the acceleration now that I know that, because I know that if I plug in 8 for t, I should get 0 for v. So I'm going to plug that in real quick just to do a thorough job of explaining this. If I solve for a now, subtract 55 and divide by 8, you get an acceleration of 6.875 feet per second squared. So what that is that's the slope on the velocity time graph. Okay, so we've graphed now the velocity function from 0 to 8 seconds. And what it asks for is the distance that's covered from 0 to 8 seconds. The distance that's covered is the area underneath this curve right here. And if you look at the units, that feet per second times seconds gives you feet. So we need to find the area underneath that curve. The area underneath the curve, it's a triangle, so 1/2 base times height works fine. 1/2 base is 8, and the height is 55. That gives you your answer of 220, and it does say include units, so be careful about that. The units in this case would be feet. There are different ways to do this. Like I said before, you can do this in your calculator if you do the integral from 0 to 8 seconds of 55 minus, in this case it'd be 6.875 t, or in this, if you're going to plug it in the calculator, you could use x and then dx here. So if you type that into the calculator, you should get the same answer, because that's finding the area underneath this curve right here. Next part says, how far does the car travel before stopping if its initial velocity is doubled? So now we're going to double the initial velocity. So what that's going to look like is this. We're going to go 110 miles per hour, and we got the same deceleration. That means we have the same slope here. If we have the same slope, and you can look at this in terms of similar triangles, if this side's twice as long, then this side would have to be twice as long too. So it's going to take us 16 seconds to stop. So one thing you could do, since we already have the equation here, you could plug in 16 right here, and you could double the speed to 110, and that would be a way to solve it. Or you can just use the area of a triangle to find the area underneath the curve, because that would be the distance covered before we stop, which is 1/2 base is 16 and height is 110. To do that, you get 880, and don't forget the units, which is feet. Next question is number 12. It says the velocity of a particle moving along the x-axis is given by this function right here. Use the graph to find the exact change in position from the particle from 0 to 4 seconds. So if this is a velocity time function, let me go ahead and graph this real quick. It starts off at 15 here, so here would be 5 and 10. And it's decreasing by 5 every second. So after 1 second, it's at 10. After 2 seconds, it's at 5. And after 3 seconds, it's at 0. 4 seconds, I'm going to have to go to -5 here. And so here's what it looks like. Now, the question says, find the exact change in position from 0 to 4 seconds. The change in position is the area underneath the curve, which is the integral. So different ways to do it. You can find the area with triangles, or you can take the integral of this thing from 0 to 4 seconds. You can plug that into the calculator, or you can do area equals 1/2 base times height, which in this case would be 3 times 15, and then subtract from that the area of the other one, which is base times height of 5. That 20 centimeters. And make sure, and don't forget to include the units right here. Okay, the next question says, on the moon, the acceleration due to gravity is 5 feet per second squared. An astronaut jumps into the air with an upwards velocity of 12 feet per second. How high does he or she go? Well, let's write a distance time equation real quick. This is off your formula sheet. Once again, it's, in this case, -1/2 gt squared is the real formula, plus initial velocity in the y times time plus initial distance. I think it's s sub 0 in your formula sheet. So in this case, normally we use we use 32 right here, feet per second. But this, on the moon, there's not as much gravity because there's not as much mass. So the gravity here would be 5. So this would be -5/2 t squared plus the initial velocity in the y, which is 12, times t, plus the initial height, which is 0. So now we've got an equation for distance and time, in case we want to write that. Now let me graph this real quick in terms of velocity and time. The velocity starts off at 12 feet per second, and then every second we're going to go down 5 feet per second. So after 1 second, subtract 5 and you get 7. So I'll say that's 7 right there. After 2 seconds, subtract 5 again, you'll get 2. So this is what the graph looks like, where the slope of this is -5, because we're decelerating at 5 feet per second squared. Okay, now this might seem weird, but to answer the question of how high, there's different ways to do this, obviously, but what I'm looking for is this point right here. And the reason why is because when someone jumps in the air, this is the distance time graph, what it would look like. At this point up here is where the velocity is 0. So at the top of the parabola, the person stops in midair for a split second. That's where the velocity is 0. That's this point right here on our velocity time graph. So that's what I want. I want to set this equation for velocity. Let me write that equation for velocity in terms of time, which we start off at 12 and we subtract 5 feet per second squared per second, which should be the same thing that we get when we take the derivative of this. So if you take the derivative of distance by multiplying the 2 down and using the power rule, you'll get this, just to tie it into what we learned about in 10.1. So there's our velocity time function, and how high do we go? Well, let's first find out the time at which we reach our maximum height, which by solving this equation, setting it equal to 0, so it'd be 12 minus 5t. So that gives us at 12/5 of a second we reach our maximum height. Now we can plug that in for this t here to find out how high that is at that time. Another easier way to do it would be to go ahead and plug in 12/5 right here and find the area underneath that curve, because the area underneath the curve is the distance that's traveled in that amount of time. So it'd be 1/2 base of 12/5 times the height of 12. And that gives us 14.4, and they've got the units here for us, feet. And then how long are we off the ground for? Well, how long are we off the ground for? We can take the time that we reach our maximum height, which we found was 12/5 of a second, and we can just double that, because if you jump off the ground in half the time, you'll reach your maximum height, and then double that time and you'll be back on the ground at this point right here. So we'll just do 24/5 of a second. Now there's other ways to do this. For example, to answer some of these questions, you could have found the vertex of this parabola right here. Now to find the vertex, you do -b over 2a, if you remember from earlier in the year. So you could have used this to find the x-coordinate for the vertex, which would have been the time that we reach our maximum height. And you could have plugged that back in to find the distance. So there are other ways to do this. You can pick a way that works best for you.